All right, today we're going to dig into a concept that's absolutely fundamental to how our world works, how things bend and stretch and squish. It's called Poisson's Ratio. Now, I know it sounds a little intimidating, but trust me, by the end of this, you'll see it happening everywhere. Let's get into it. So let's kick things off with a super simple question. When you stretch something, I don't know, a rubber band, a piece of gum, whatever, what happens to it? I mean, the obvious answer is it gets longer, right? And yeah, that's true. But that is only half the story. You see, whenever you apply that pulling force to an object, there are actually two different things happening at the exact same time. And understanding both of them, well, that's the key to unlocking what Poisson's ratio is all about. Okay, so as you pull on something, you create what engineers call longitudinal strain. That's just a fancy way of saying it gets longer. But at the exact same time, it also experiences lateral strain, meaning it gets thinner in the other directions. And, the reverse is true too. If you squish something, it gets shorter, but it also gets fatter. So if things get longer but also thinner, it just makes sense that there be a way to measure the relationship between these two changes, right? And of course there is. That is exactly what Poisson's ratio does. It puts a number on this whole effect. So let's get the official definition on the table. Poisson's ratio, and you'll see it represented by this Greek letter nu, is simply the ratio of that sideways squeeze to the lengthwise stretch. That's it. It tells us precisely how much a material is going to shrink sideways for every little bit it stretches long ways. And the formula for it looks really simple because, well, it is. You just take the lateral strain, how much it got thinner, and you divide it by the longitudinal strain, how much it got longer. But hang on, you might be looking at that negative sign out front and wondering, what's that all about? That negative sign is actually just a clever little trick to make our lives easier. Think about it. The length is increasing, which is positive, but the width is decreasing, which is negative. So one of those strain numbers is going to be negative. The minus sign in the formula just cancels that out, so our final Poisson's ratio is a nice, clean, positive number. It just tidies things up. Okay, theory is one thing, but let's be real. The best way to really get a handle on this is to see it in action. So let's just do a quick, simple calculation and see how this all works in practice. Let's walk through this together. So we start with a metal rod. We know its length and its diameter. Then we stretch it, and we measure exactly how much longer it got and how much thinner it got. From there, we just calculate the two strains separately, the lengthwise one and the sideways one. And for the final step, we just plug those two little numbers right into our formula. You run the numbers and boom, you get 0.2. That single number is the Poisson's ratio for this specific material. An engineer can look at that value and instantly know a ton about how this metal is going to behave when you put it under stress. It's like a personality trait for a material. But 0.2 is just one value for one material. Different materials act in totally different ways, which means they all have their own unique Poisson's ratios. And this creates this fascinating spectrum of behavior with some really cool examples on either end. So let's look at the extremes. On one end, you've got something like cork, with a Poisson's ratio that's almost 0. This is why it's so perfect for a wine bottle. When you shove it into the neck, it doesn't bulge out on the sides and get stuck. Now, on the complete opposite end, you have rubber, with a ratio right around 0.5. This means when you stretch it, its volume barely changes at all. It just rearranges itself, getting longer and thinner in almost perfect proportion. So at this point, you might be thinking, okay, that's a neat little physics trick, but why does this actually matter in the real world? Well, it turns out this little number is incredibly important, especially if you're building, well, anything. Here's the bottom line. Poisson's ratio is a cornerstone of engineering and materials science. It's the number that lets you predict exactly how a bridge beam or an airplane wing is going to bend into form when a load is put on it. But it's even more fundamental than that. It's like a master key that connects a bunch of other critical properties, things like stiffness, elasticity. It's all tied together by this one simple ratio. And just to give you a feel for this, check out where some common materials land. You can see strong, rigid materials like steel and aluminum are kind of in that middle ground, around 0.3. That tells us they have this really predictable, moderate amount of sideways shrink when you pull on them, sitting right there between the extremes of cork and rubber. So here's my challenge to you. The next time you pick up a rubber band, don't just notice how long it's getting when you stretch it. Take a really close look at how much thinner it's getting at the same time. You're not just fidgeting with an office supply. You're actually observing a fundamental property of our universe right in the palm of your hand. You are watching physics in action.